computer decided to explode this morning, and so I've been trying to bring it back to life, not very successfully, but so I'll let you start.
So we prepared a short list of questions that we thought kind of represented some open topics that came up in the talks today. But perhaps before we focus on the questions we selected, we could ask the audience, are there questions you have that you would like to begin the discussion with? Suggest your own questions or pick
Well, one of the arguments which I showed in my talk and is in Genzer et al. 2000 is that it's also the slope of the profile is not consistent with NFW. If you believe the argument that led to this. So it's not only evidence of baryons, it's also the slope of the profile of the dark matter, which is consistent with the dark matter deficiency, as if the dark matter was pushed out. That's my comment on the first question. I said that the argument is that there's both a depletion of dark matter, deficiency of dark matter, as well as the profile not being an FW, but rather a flatter profile. Well, in some sense, it's relative, right? The baryons and dark matter are relative. So in some sense, it's not clear whether there's a big difference, but I'm saying that it's also the slope of the density profile.
You see need for an explanation, or what is? I mean, okay. Let me try again. The general goal of this rotation curve work is you measure as best as you can the beam corrected rotation curve in the frame of the galaxy. You have a dynamic model which consists of a stellar component, a dark matter component which you assume to be NFW in the way we start. And then you fit that rotation curve with these dynamical parameters to the quantities you want to determine. And since the dark matter content naturally would have to increase, you would naturally expect that the rotation curves, as we know from low redshift, are at least flat, if not increasing. And the remarkable thing is what we found already in some of the earliest galaxies, that this is not generally the case, especially at the highest redshifts. Now, having said this, the explanation for this, in part, could be a mistake in the observation, of course. But the mistake, the explanation is in part what we call asymmetric drift. Is because the velocity dispersions are large, and as far as we know, they do not change all that much with radius. That means the pressure component becomes larger and larger as you go out in an exponential disk, and therefore, even if you don't do anything, so to speak, the rotational part of the component must go down. So when you make the model, you take that into account. You must take that into account. Otherwise, you would get zero dark matter out to very large radii. But it doesn't help in those galaxies where we see that you still don't get the kind of increase in apparent dynamically seen matter content you would expect from an NFW, and so that sets your limit on F dark matter.
I think we can take the question.
So the second part of your question was what happens to the dark matter cores at low redshift? Some of these massive galaxies will end up as the central galaxies in clusters or big groups. And there's a standing issue on that. It goes back at least to more than a decade ago, papers by Sand and Ellis, Richard Ellis, followed up by a number of papers by that group and other groups. What they did is they carefully subtracted, they measured and subtracted the mass of the baryons, which are stars in these galaxies, and dynamically measured what the total mass was and found there was very little mass contributed by dark matter, even much less than in normal galaxies. And they found this in many central galaxies in groups and clusters. So I think that partly answers the question of what happens to the dark matter cores at low Z. They're still there. And of course, the theoretical response was to appeal to AGN, and as Avishai has argued, yeah, AGN will do the job, but you need to set up the initial conditions right for the AGN to be able to do it, and that may require heating of the dark matter by dynamical friction or the kinds of things that Avishai suggested. I think it's still quite an open question to follow these galaxies from redshifts of 2 or so, where you're seeing this phenomenon at high redshift, down to low redshift. And I think that's still an open question.
You had a plot. You had a plot. And I said,
Empirical evidence from most of the low redshift passive galaxy observers is indeed that they are low dark matter content. I mean, that's for sure. And they are the descendants of the high redshift massive star formation population. But I should say that there is the sample called Virial, which Trevor Mendel has worked on, which is at redshift 1.7, and that gets pretty much the same results. And that would be consistent with quite a fraction of the massive star formings at redshift 2 already going over into the dead valley by redshift 1.7.
Maybe I'll add a follow-up question. So the mechanism that Avishai described, I think he told us it operates primarily at high redshift. Given that, is it surprising that the cores would survive? Namely, do you not expect them to regrow over time? As maybe there's more accretion of dark matter or mergers of halos, or do you, if you form them at high redshift, do you really expect them to survive for a long time? Maybe Avishai.
But it's a continuous process.
Yeah.
Both the accretion of satellites and AGN feedback is a continuous process. AGN can be thought of as
Yeah.
and the accretion is continuous as long as it's high, namely as long as you're above redshift 1 and above the critical mass, it's expected to be maintained, like by the bitter and hot, and that is also
Yeah.
passing outflow should keep it.
Yeah. But past redshift 1, do you expect the core to be frozen in time or to redevelop a cusp?
Well, then there is a frozen in some sense, there's much less accretion, so there's less reason for contraction. It's an anticipation less, and it can be just dark halos of massive elliptical galaxies.
I have a very innocent question. That is, what happens when you have cooling flows? I realize that may be special conditions, but in cooling flow situations, you don't have a dark matter that is, dragging the gas down. Presumably the gas is responding purely to the total structure of a, let's say, center of rich cluster. I assume that in those cases you do build up baryons without any comparable buildup of dark matter. Am I understanding what happens in cooling flows? When you have cooling flows in the hot gas, I presume that the cool gas that falls out of that then concentrates to the center of the potential well. And to my knowledge, I don't know, maybe I don't understand dark matter, but I don't see why that material, unless it's really, really has a huge amount of gravity somehow, it doesn't pool an associated amount of dark matter. So wouldn't that contribute to also a, pardon? Yes. So wouldn't that contribute towards? Yeah. Okay. And then similarly, also when you have two satellites that collide with each other around another galaxy, say, et cetera, again, the dark matter could travel in a totally different path than the gas, which is collided, and therefore they get blocked. It's sort of like the bullet cluster. In that situation, I also see that you can contribute baryons to the central region without the dark matter again occupy the same region. I don't know what you call that. You call it baryonic dynamical process or something like that. Is that also true? I'm really asking this as a pure, trying to understand what happens in these situations. What do theorists say about that? But it does occur. We know that. So.
So that process that you described appears to be the explanation for these rare galaxies, the small dwarfs, with apparently almost no dark matter, no evidence, no dynamical evidence for dark matter. So this was proposed by various theorists, and Peter van Dokkum seems to agree that that fits the observations of these things. This phenomenon was called the bullet dwarf phenomenon. So it's like the bullet cluster, where the gas, of course, stops. There's a gas shock, but the dark matter, and for that matter, the stellar galaxies just keep moving.
Yeah, the difference between
So,
that,
but this is.
I'm talking about using that mechanism to feed baryons into the central potential well without the.
Yeah. So this certainly worked for this particular set of dwarfs, and seems to have solved, yet another potential problem for cold dark matter. Looks like it really works, but I don't see how this could work for massive galaxies. The thing is that they've already turned a lot of their mass into stars. I think just a couple quick comments. If you merge galaxies with cusps, you get a cusp. If you merge galaxies with cores, you get a core, you don't get a cusp. The only way you can get a cusp is with dissipation, which means they have to be very wet. But at the centers of clusters, once you've already formed a massive galaxy, you don't have a lot of gas left. So the dissipative process isn't going to regrow cusp. Anyway, if it did, it would be in the baryons, not in the dark matter. So, but probably one of the problems is that it takes big box simulations or high resolution massive simulations to make massive galaxies and follow them down where they become the centers of groups and clusters. You've got to simulate the whole thing, and that takes a lot of computer time, and I'm not sure it's really been done. So I think there's still some open questions, but it doesn't, my own guess is, I don't think it's a problem if you can start by solving the problem that Reinert and colleagues have been showing us exists in trying to understand these galaxies at high redshift, which are quite common, that seem to have much less dark matter than an NFW cusp.
Linda, I wonder if we should, there was a comment, a question from Sandy, and I guess we'll take that, but I wonder if after that we could consider moving to question number 2. Yeah.
We just saw a very high resolution simulation, and I wondered if the authors of the simulation had looked at the dark matter profile in it at early times.
About the Milky Way mass galaxy, that's not one of these massive ones.
Right, yeah, you need a bigger one.
Could somebody repeat that?
The simulation was for a Milky Way mass galaxy, and the things that we were talking about are not going to become Milky Way mass galaxies. They're much more massive than that.
Okay. Andrew, maybe you have a
Redshift.
response to that?
Well, I just want to add first of all, a purely observational data point, which is that in the Milky Way itself, where we can measure stellar dynamics quite well, and some people, like Ortwin Gerhard, who's done some very nice modeling of the dynamics of stars in the inner Milky Way. It's hard work because we're looking at the bar, but nonetheless, if you talk to Ortwin, he claims pretty strongly that the Milky Way has about a 2 kiloparsec core in the dark matter profile. And some Milky Way simulations do. If you look at ours, they're very cored at high redshift, which is the same process that we see happening in our low mass galaxies. Some of them can still have quasi-cores at redshift 0. It's not ubiquitous, but some of them can. So this is not just, it's not obvious this is just a massive galaxy phenomenon. There is evidence for it in the Milky Way as well.
A comment about the survival of the dark matter cores. I think some simulation shows that the last major merger can regenerate central dark matter cusp. But I guess major mergers are more rare for massive galaxies. So I guess it might be easier for dwarf galaxies to regenerate cusp according to their growth history and merger history. That's what I guess.
Shall we talk about turbulence in the interstellar medium? Linda, may I let you maybe formulate the question in the way you'd pose it? And it's a question we both had.
I don't know, the question number 2, for me it's really reassuring to see that that observations are addressed by these theories now of turbulence. But I don't know, maybe there are second order effects that we need to think about, but I felt that was really a lot of progress, at least since the last 2 to 3 years when we were all sitting together the last time. But I don't know, are there any comments from the audience on this?
Well, that's exactly what Omri's talk was addressing.
Right, exactly. I mean, yeah.
Maybe we have this question asked by Frank. So, the role of gravity, while on a micro scale, how exactly is that energy transferred from potential energy to kinetic energy is maybe not so easy to answer. However, there are simulations of pure disks with no star formation, no feedback, no nothing, that are able to, and only self-gravity, that are able to sustain supersonic turbulence for long periods of time. So the only source of energy there, they are completely isolated, is gravity. And one might think, so for example, one of the attempts to address this is either by viscous stresses. When you assume turbulence, when you model it as a effective viscosity, or when you look at, for example, the work done by Avishai, and the encounters between the clamps and the disks themselves, they tend to stir up the turbulence, and you don't really need anything else but gravity to do that. So this is to answer both Frank and, which I assume what inspired the second point. On a micro scale of exactly how this process works, I don't really know. But on a global scale, I think gravity is able to, and it has been shown way before me and others, that gravity is able by itself to sustain turbulence to some levels. So just to comment on that again.
I think this was a question raised by Frank during one of the talks. You start with large-scale perturbations in a disk. These large-scale perturbations, by encounters or by tidal torques, they generate dispersion velocity, which we call turbulence. And it has coherency because the structures are big, spiral arms, bars, big lamps, etc. Now, you generate turbulence, and you also push out angular momentum. It's a well-known effect that such tidal interactions, it's known from physics of planetary disks. You push angular momentum out and you pay for it because of angular momentum conservation by mass transfer inwards. Now, as you fall inwards, you fall into the potential well. This is a gain of gravitational energy again. So the whole balance is that this is the source of energy. But the direct mechanism has to do with the torques pushing the gas around from clean rotation.
I think we have to be careful with, I think what confused me is the word turbulent, which means something very specific for me. I think I agree with everything you said, and gravitational instabilities create torques and disturbances, and they create non-circular motions. And non-circular motion is not the same to me as turbulence. And I think, as long as we agree on that part, then I'm fine.
So I guess for me, one of the questions, so this is a question that I've thought about from a theoretical point of view, and I've tried to figure it out, and I'm still not sure how I'm going to convince myself of what the answer is, because the theoretical calculations I've been able to make, they typically tell me that there's enough energy available through a variety of channels like gravity or stellar feedback, and the uncertainties are big in kind of the dimensionless efficiency factors that enter in the calculation, like the dimensionless efficiency factor for the conversion of stream energy into turbulence that Omri presented in his talk. And so I was wondering if anybody has kind of different ideas for how we might get at this question of what dominates the turbulence, maybe beyond the kind of analytic models we've been thinking about. So how do we move past the large uncertainties in these like dimensionless prefactors that enter in our theories, and actually convince ourselves we've figured out the answer?
I'm always surprised with some of these discussions, because to me, it's if you remove the cosmic web feeding of the disk, then whatever's going to happen, you can sustain it for a little bit, and then it's going to die out. The system will self-adjust itself, and that's it. So ultimately, to me, the answer is what drives the system? It's that damn accretion from the cosmic web. You take that away, give it another 2 gig years, and it's done, doing what it's doing. It finds an equilibrium. So I find it somewhat of a moot discussion. Cosmic web accretion, that regulates the whole thing. Bob the model. Sorry?
Then it wouldn't drive turbulence at all. It just adds mass, but it won't drive turbulence. So it cannot be the only mechanism. And
It's the mass accretion, even if it's smooth, that builds up the disk until it goes unstable again, and that creates the torques, and that creates the inflow. If you remove the mass accretion, the system will come to a halt dynamically in about a dynamical time.
that's because the disk will disappear, yes.
Mass accretion is crucial.
Yeah.
But it's not a direct driver of turbulence necessarily.
Not necessarily direct drive.
Here, you had a comment?
I mean, maybe slightly related and slightly not. Do people think there is any one-to-one correspondence or any way to formulate a relation between the turbulent state of the ISM and what drives that, and the turbulent state of the CGM and what drives that? Does one require the other? Can we learn anything about one from analysis of the other? Okay, good.
That's very good.
Yes. Sandy.
Do magnetic fields help?
there. I remember papers from Eva Stracker's group from about a decade ago that in some regime you can have the magnetorotational instability, I think in the outer part of galactic disks. I suspect this is a subdominant contributor to the turbulence we typically observe in galaxies. But
yeah, I mean,
Tom.
actually, to your question, with the magnetic fields on the core scale and sort of the molecular cloud scale, many numerical experiments now show it's very helpful, actually. Particularly when you take young stellar outflows, jets, without the magnetic fields, they completely leave the cloud. You have actually no coupling. You don't get any steering of the turbulence. But as soon as you have the magnetic fields, even these very directed, very thin jets will actually dissipate a lot of their momentum and share it with the whole cloud. So fundamentally, on the very small scales, I think the way feedback couples back and allows to sustain supersonic turbulence, B fields are totally essential. I think it's useful.
I'm a bit out of my element here, but I'm going to channel my wife, Sharon Might, who recently put a paper on Archive expanding on the work by Goldreich, Lyndon Bell, 1965, which is the last time that anybody did calculations on instabilities in three-dimensional disks. So she generalized perturbations in 3D disks, and she finds that in the midplane you get instabilities on the gene scale, purely, yeah, and these instabilities can be driven by star clusters or, anything that perturbs the disks, and then you get genes-like instabilities in the midplane, creating molecular clouds because they're on that scale. Without any magnetic fields or anything, just pure gravitational instabilities from first principles in rotating disks with some finite thickness. Depends on the shapes of the instabilities. Are the perturbations even, uneven, truncated, not truncated? It's all in there. I don't understand most of it, but yeah, have a look at it.
So it sounds like an elaboration of the standard tumor instability picture, but more exact calculation with finite.
Tumor is
finite.
a element of one of the.
Okay.
Tumor is a thin disk.
Yeah.
This is 3D, full 3D.
Yeah. How are we doing on time? Oh.
Thank you. So is there a consensus on the origin of the angular momentum of large disks? So we heard that indeed, without infall of intergalactic matter, within some number of 100 million years, the galaxy will die, and we know that it's crucial to take into account the mass coming from the outside. Now, if there was a debate whether it's only the mass that brings energy and then turbulence, or in the simulations, if you take out the infalling matter, can you produce the large disks and the angular momentum that you see there? Or because I'm referring here to recent findings of galaxies with large V over sigma, and some people have been claiming that it may be the angular momentum can be induced by some accretion. So as an observer, I'm just wondering whether accretion is important or not in building the angular momentum of galaxies, or if it's just a secondary parameter.
I'm not sure I understand the question, because without accretion, you're not going to have a galaxy in the first place. So you must, but you must have I must be misunderstanding the start. Yeah. Do you see what
Well,
so I'm not sure how you can have galaxies without accretion. So are you?
So you're saying that then the angular momentum is completely driven by accretion?
It's brought in by the matter that's assembled into galaxies. So,
okay. So no, I didn't know if it was obvious for everybody. For me, I don't know. I'm an observer. So just I was wondering whether you could have some accretion of gas, and then in a second stage you could have the angular momentum built
Yeah.
just by instabilities or like flyby or whatever, or if it's the energy of the matter that is infalling that is bringing angular momentum or not. So that's my question as an
Okay,
observer. I don't know what's the consensus on that, or maybe the question makes no sense.
I mean, I think in the standard picture, it's the angular momentum primarily comes from the gas and the mergers that bring baryons to the center of halos. But
You mean
I'd be
the
curious to see
infalling
what.
gas or the mergers? Is it the same thing?
Well, I think both can contribute angular momentum to a galaxy. So the infalling gas from the intergalactic medium comes with net angular momentum in general, and that can form, say, disk galaxies. And then when you have mergers of galaxies, that there's also angular momentum involved, and that can contribute to angular momentum of the final system.
So if I just continue
Also,
my question. So in the simulations, cosmological simulations, building large thin disks is no more a problem than you're saying.
It certainly has happened. It is happening in many simulations. Whether we have reached the end of the road in terms of realism and understanding why that is, probably not. But we do form large thin disk galaxies in many
because
of the
when I
latest
read
high-resolution
from an
simulations.
observer
Yeah.
perspective the TNG simulations, for example, and other, I think they didn't have large disks.
Did or did not?
They didn't have large thin
large
disks.
disk. Okay.
So that could be connected to the
Okay,
question of the turbulence in some sense.
Okay, thank you. Others may have thought on this topic, and so feel free to raise your hand if you have an answer for David.
Otherwise, yeah, we're past our nominal time. We didn't finish all the questions, but then